If somebody ran into the room at 5 miles per hour, what is that person's velocity?
It depends on which direction they're going.
Into the room, this way.
Depends which, like, way that's defined.
Let's make that, how do you want to define it?
I guess I.
Okay, or I hat? Yeah, all right, so let's make that the I hat direction. So what's the velocity?
5 miles an hour, I had.
Is there another answer? What? Sorry, let's rephrase that. There's another answer. What else could it be? Or, alternatively, tell me what 5 miles per hour I hat means. Actually, it's the 5 miles per hour that I care about. What does 5 miles per hour mean?
That if he keeps moving at that consistent velocity and over an hour, he's gonna move 5 miles.
You see?
Not practically speaking, but
Right, well, we're in a classroom setting. We can do the ideal here.
yeah, if you just ran right through that wall in every obstacle, if you considered it at the same velocity, you'd move.
So how fast are you going? Let's just deal with speed. What's your speed?
Oh, I see what you,
So what am I getting towards?
it's all about relativity.
Galilean relativity, we're not getting into the special stuff. All right. Excuse me, I have a cough drop in my mouth. When you say someone is going 5 miles per hour, what is generally understood?
Usually relative to the surface they're standing on,
Okay,
or the ground.
but there's nothing absolute about that. This is one of the big points of, is there something that you could universally call zero, that it's not moving, and do all velocities based on that? And that's where special relativity comes in, where the answer was them. But the physics should still hold regardless of the reference frame, regardless of how fast you're moving. I should be able to work out the physics. Momentum should still be conserved in this problem, and kinetic energy should still be conserved. So I've got a 3 kilogram mass going at 6 meters per second in the positive direction. I got a 4 kilogram mass going to the left at 2 meters per second. So I got, this is 1 and 2. So M1, let's see, do it this way. The initial velocity of 1, P1, V2, P2, and then my total momentum. So my initial velocity this is 6, this would be 18. Let's do units. We are not savages. And this is -2, this is -8, and that's 10. That's what we did before, and that's why I just sort of threw it up there. Any questions about where those numbers come from? All right, suppose you are in the 3 kilogram box, or you got a camera in there in the 3 kilogram box, and so from your point of view, you're not moving at all. So if you're from the point of view of this, or this is what we call the lab frame, we got these two objects coming towards each other, going at those velocities relative to the ground. But if I'm traveling along at the same velocity as the 3 kilogram, it doesn't look like it's moving to me. So this first one we're going to call the lab frame. I don't know how well that shows up on video. And then if I went to the 3 kilogram frame, this is going 0 meters per second. Therefore, what is its momentum?
0.
Kilogram meters per second. What is the velocity of the 4 kilogram mass now?
-8.
-8. And so what is the momentum?
Negative. Oh, 32.
Yep, -32. So my total momentum is -32 kilogram meters per second. So my total momentum changes just by changing my reference frame. Let's do the 4 kilogram mass. On the 4 kilogram frame of reference, its velocity is 0. Its momentum would be 0. How fast is the 3 kilogram mass going from 4's point of view?
8 meters per second.
And therefore, its momentum,
32 meters per
3 kilograms.
24.
So we can set our initial momentum to almost anything we want. I want it to be 0. I want my total momentum to be 0. So how fast do they need to be going? Well, recognize as we shift frames, all we're doing is just adding or subtracting a velocity. If I go from here to here, from here to here, I just subtracted 6 to get to the new velocity. To get from my initial lab frame to the 4 kilogram frame, I added 8. Try that one again. Oh, there we go. I added 2. So as long as I add the same velocity to another reference frame's velocities, then I've got another frame where momentum is still conserved. So in my 0 momentum frame, I know I'm going to change my initial velocities by the same amount. So I know that 3 times 6 minus v, v is what I'm trying to figure out, plus 4 times -2 minus v is equal to 0. So I'm trying to figure out how much do I need to shift each velocity so that my total momentum is 0. Well, it's an algebra problem. 18 minus 3v is equal to plus -8 minus 4v is equal to 0. 10 is equal to 7v. V is equal to 10/7 meters per second. We've run across 10/7 before in this context. If you took notes, or if you watched the video, where did 10/7 pop up before? I guess it's all down to you, Patrick.
You must have skipped that step.
Okay. Well, 10, where did we run across 10 before?
Moment.
Of, did you say it and I just didn't hear you?
No.
Okay. It is a momentum
The total
of,
system of both things.
in the lab frame. Don't forget, my momentum can change depending upon how fast I'm traveling as an observer. In the original framing, that was the momentum. 7 is my total mass. What problem would I set my total momentum equal to my total mass times the velocity? It was the first problem we did with those two masses. I don't want to spoil it. I know I saw it over here.
That was an inelastic.
The perfectly inelastic. This is the velocity of the perfectly inelastic solution. The final velocity. So they have the two objects, they stick together, it's how fast they are going. So this is sometimes referred to as the center of mass frame, or the zero momentum frame is how I usually call it, what I usually call it. So how fast it's going here is 6 minus 10/7, which is 32/7. The momentum, that times 3, 96/7. The other one, it's -2 minus 10/7, which is -24/7, which gives me a momentum of -96/7. Fortunately, those are opposite signs to each other, so my total momentum is 0, as we were trying to get. In case you missed it, this is the solution to perfectly inelastic collision. And there are many times when I've given a setup where they got the two masses heading towards each other, they will collide in a one-dimensional collision. First question, if it's a perfectly elastic collision, what's the final velocity? Second question, if it's perfectly elastic, what are the final velocities, plural? Now, we have our zero momentum frame. So in this frame of reference, I've got my 3 kilogram mass heading this way at 32/7. I'll leave it as the fraction, 32/7 meters per second to the right. I've got my 4 kilogram mass heading to the left at 24/7 meters per second. They're going to collide. They have a certain amount of kinetic energy right now. They're going to collide, and after this collision, I know that my momentum still has to be 0, and my kinetic energy still has to be the same. So, this is before, and then after. What is a solution in the zero momentum frame? A solution where the total momentum is still 0 and the kinetic energy stays the same. Let's deal with a less abstract. I got my 3 kilogram going at 6 meters per second. I got a 9 kilogram going to the left at 2 meters per second. Total momentum is 0. Kinetic energy cares about speed, momentum cares about velocity. What would be a solution for this so that my momentum is still 0, my kinetic energy is still the same? All right. Just giving you a chance to show off here. Apparently, you're all just being modest. Here is a solution. So again, before, after. If my speeds for each object, if the speed for each object doesn't change, then the kinetic energy is going to stay the same. Because kinetic energy depends on speed. All I've done is I kept the speed the same, just flip the sign. My momentum is still 0. Instead of having initially the momentum of 18 units and negative 18 units, afterwards, all I've done is flip the signs. My sum is still 0. So over there, after the collision, well, if my 3 kilogram mass is going to the left at 32/7 meters per second, and this one's going to the right at 24/7, and then the final answer has to be in the same reference frame that we started with. Well, to get out of that reference frame, to get from here to here, we subtracted 10/7. Now to get back, we just reverse that. We add 10/7. So my 3 kilogram mass is at negative 32/7 plus 10/7, which is negative 22/7. Which is negative 3.142857, etc. meters per second. And for my 4 kilogram mass, it's 24/7 plus 10/7, which is 34/7, which is 4.8571. Which is the same answers that we had before. We'll work through one more problem like this, showing the notation that I typically use. And then you will work one in whichever format you like. Questions before I erase at least this?
So for this whole thing, all we did was combine the 2 reference frames and have different speeds, and then solve it, and then undo that change.
Pretty much. All right. Let's tackle a new problem. So again, 3 kilograms going to the right at 4 meters per second. I'll have a 9 kilogram going to the left at 1 meter per second. Try that one again. Scratch that. Six kilograms going to the left at 1 meter per second. All right, so the way I generally set it up, 3 kilograms and 6 kilograms. My initial velocity in the lab frame, so I'll just put a little L for lab frame, 4, -1. I need to shift out of that frame. I want to go to the zero momentum frame. So we shift to the zero momentum frame. Well, my total momentum is 12 minus 6. And that's going to be equal to, well, perfectly inelastic collision, they stick together, so that's going to be equal to 9V. V is 2/3 meters per second. So I'm going to subtract 2/3 from each solution. So this is 3 1/3, and this is -1 2/3. We have the collision. Signs flip. So this is now -3 1/3. This is +1 2/3. This is still the zero momentum frame. We need to shift back to my lab frame. Well, I subtracted 2/3 to get out of it. I have to add 2/3 to get back in it, plus 2/3, plus 2/3. And so that becomes 2 4/3, no, 1 4/3, or 2 1/3 meters per second, positive. And this one becomes -2 2/3. So before and then after, and those are not the numbers I was expecting, so did I mess up somewhere?
Oh, well,
Did I mess up there? So, oh,